This video is on electron configuration and describing the most probable location for an electron using the first two quantum numbers. So as we talked about last time in describing that quantum mechanical model, that we do have energy levels where we have electrons that exist in certain distances from the nucleus, which vary because of energy. We also can break down each of those energy levels into sublevels. Those sublevels or orbitals are mathematically drawn areas of probability where we can describe the most probable location for an electron. And we named the sublevels based on the shape of that mathematically drawn area of probability. So we started in the last video talking about each energy level and the maximum number of electrons that each energy level could hold. Now, I expect that you know this from middle school, but we're going to layer in the sublevels that exist in each of these energy levels. The first energy level can only hold 2 electrons and only has an s sublevel. So it's only a sphere shape, mathematically drawn area of probability there on that first energy level. The second energy level can hold up to 8 electrons and it has s and p. So it has its own s sublevel. So that's a sphere, just like in the first energy level, but a much larger sphere because it's on the second energy level. And it also has a p sublevel. So in addition to a spherical mathematically drawn area of probability, we'll also have one that's shaped kind of like a dumbbell. The third energy level can have S, P, and D sublevels, and the fourth energy level has all 4 sublevels, S, P, D, and F. Now, this is what something would look like where or an atom would look like in its mathematically drawn area of probability if it were to have the first and second energy levels filled. So you would have this spherical shape on the first energy level, a larger sphere for that second s orbital on the second energy level, and then it has a p sublevel, which is shaped like a dumbbell, but in 3-dimensional space, you have 3 different orientations of that, and we'll talk about that here in just a minute. So this would be all of the p sublevel orbitals, again, what their shape is. And then here is what it would look like. And these are mathematically drawn areas of probability where an electron is most likely to be found. So you can see the 1s there underneath, the 2s is here, and then that 2p are these lobes that kind of stick out here. This is an actual hydrogen atom, and I just wanted to show you that. This was a pretty awesome picture, but you can kind of see it's showing electron density, and you can kind of see the energy levels of an atom. That was kind of neat. All right, so now let's talk about each of these mathematically drawn areas of probability, which we're going to call our sublevels. That spherical shape is an S sublevel, and that one has the lower energy. So this table has sublevels in order in which they're going to fill. So S always fills before P, which always fills before D, which always fills before F. It's also in increasing energy, and that's the reason why it fills that way. You're going to find that electrons are pretty lazy and they don't want to exert any more energy than absolutely necessary. So they're going to always fill the one that requires the least amount of energy out of them. You might can relate to that. I do. So the S sublevel, that spherical shape, can hold a maximum of 2 electrons. And in 3-dimensional space, it only has 1 orbital orientation. No matter which way you turn the sphere, it's always going to look like a sphere. So the shape doesn't change. So in 3-dimensional space, there's only 1 orbital orientation. Now here in this picture, I have a 1s, a 2s, and a 3s. On the different energy levels, you can see they get larger and larger. Now, the P sublevel in general has this kind of shape. If you just look at the electron density, we generally simplify that and say this shape looks like a dumbbell, like what you would lift weights with. And the P sublevel can hold a maximum of 6 electrons. and it has three orbital orientations. So in three-dimensional space, this dumbbell shape could be oriented along the x-axis, along the y-axis, or along that z-axis. And that's what gives us our three orbital orientations. The d sublevel can hold up to 10 electrons, and it has 5 different orbital orientations in three-dimensional space, most of which look like a four-leaf clover except for this weirdo. Then the F sublevel can hold up to 14 electrons, and it has 7 different orbital orientations. I say it looks funky, or like a flower, whichever you want to go with. Now, how do some of these numbers relate? Well, if you'll notice, this column is half this column. So that means 2 electrons can fit in each orbital orientation. If I go back to P sublevel, it can hold up to 6, and there are 3 orbital orientations. So that means you can have 2 electrons in this orientation, 2 electrons in this orientation, and 2 electrons in this orientation, giving you a total of 6. Okay, other things that I want to talk about. So the first energy level only has an S sublevel, and its 2 electrons are in that S sublevel. The second energy level can hold up to 8 electrons. It has an S and a P sublevel. 2 electrons would go in S, and then 6 electrons would go in P. If I add these two together, I do get 8. And then if I have SP and D sublevels on that third energy level, I can hold up to 18 electrons. 2 would go in the S sublevel, 6 would go in the P sublevel, giving me 8, plus 10 more in the D sublevel. Now, electron configuration that we're going to start drawing shows the number of electrons in each sublevel. So really, we're only going to deal with 2 of the 4 quantum numbers, the energy level and the sublevel. Now, ordinarily, a sublevel is filled to capacity before the next one starts to fill. I like to think of like a champagne fountain, where you stack champagne glasses and then you would pour champagne into the top glass only. And the top glass fills up and then spills over and fills up the next level, which then spills over and fills up that bottom level. So that's kind of how the electrons are going to go. They are going to fill a sublevel to completion, and then the next one would start to fill. Now, which one is going to fill first? Well, I've kind of already alluded to that. And this is actually a pretty important principle for us, the Aufbau principle. The Aufbau principle says that an electron occupies the lowest energy orbital that can receive it. What that means? Electrons are lazy, and they don't want to have to exert any more energy than absolutely necessary. So they're going to fill the lowest energy orbitals first before they fill any that are higher. So those lazy electrons. All right. So let's look at an electron configuration and what it means. So I'm going to start with this atom of carbon. Now, we're not going to be drawing atoms very much, but this is good to link prior knowledge to what we're going towards. And when we describe these electrons, and carbon has 6 electrons, 2 in the first energy level, and then 4 in the second energy level. So if we look at this, we're going to describe the electrons closest to the nucleus first, so on the first energy level. So we're going to describe these 2 that I now have highlighted here in red. And so this first thing I want to mention is its energy level. Well, this is the first energy level, so I'm going to put a 1 there. The first energy level only has an S sublevel. So what we're going to write next is the sublevel, and that would be an S sublevel. Then what we need to describe is how many electrons are in that S sublevel. Well, we know an S sublevel can hold up to 2 electrons, and I happen to have 2 to go in there on that first energy level. So I'm going to write a 2 here. If I only had one, I would just write 1. But in this case, I do have 2 electrons on that first energy level, so I'll count both of them. All right, so this is electron configuration and what each of them mean. All right, you may want to add this to your notes. First energy level, then sublevel, and then the number of electrons in that sublevel. Okay, so we've only described 2 electrons though, and we've got 4 more to describe here for carbon. So let's keep going. Again, I'm going to follow this progression for the rest of the electrons. Let's start with these 2 right here. So they are on the second energy level. The second energy level has S and P sublevels. S requires less energy, so S fills first. And you'll find S always fills first. S sublevel can hold up to 2 electrons, and I have 2 to go in there. All right, so we've described these 2 electrons. Now let's try the last 2. They are still on energy level 2, so I have to write another big 2. I don't know why, you just do. Then, which sublevel are these 2 electrons going to be in? Well, they're on the second energy level. The S sublevel is already full, so the electrons are going to go into the one that has the next least amount of energy, and that would be a P sublevel. So after S is full, P would then fill. So these electrons are going to be in the P sublevel. And the P sublevel can hold up to 6 electrons, but I only have 2 that need to go in there. And so I'm just going to write a 2. All right, with carbon's 6 electrons, we can see that these are the number of electrons in each of those sublevels. And if I've completely described all of them, it should add up to the number of electrons. So 2 plus 2 is 4, plus 2 more is 6. I had 6 electrons in carbon, and so I'm done here with that one. This is the electron configuration for carbon. Let's try another one with more electrons. So let's look at chlorine. Again, we're going to follow this progression right here. So we want to start with the electrons closest to the nucleus. These are the ones that I have highlighted here in red. They are on the first energy level. The first energy level only has an S sublevel. And an S sublevel can hold up to 2 electrons, and I have these 2 to go in there. Now, let's try some more electrons. So on the next 2 that we're going to look at, they're on the second energy level. Second energy level has S and P sublevels. So S requires less energy, so it's going to fill first. An S sublevel can hold up to 2 electrons, and I have 2 electrons to go in there. Now let's look at these electrons. They are still on the second energy level. The S sublevel is full, so the electrons are going to go into the one that requires the least amount of energy that is left. And so that would be the P sublevel. And the P sublevel can hold up to 6 electrons, and I have 6 right here to go in there. Now let's look at these 2. They're on the third energy level. Third energy level has SP and D sublevels. S requires the least amount of energy, so it's the one that's going to fill first. S can hold up to 2 electrons, and I have 2 to go in there. Now let's look at the rest of these electrons. They are still on the third energy level. The S sublevel is full, so now the P sublevel will start to fill. And the P sublevel can hold up to 6, but I only have 5 more electrons, so I'm just going to put a 5 here because that's how many electrons would be in that P sublevel. This is the electron configuration for chlorine. So you can kind of start to see a little pattern here, that 1s and then 2s, 2p, 3s, 3p. And it would be great if that pattern continued. But there's a little bit of an issue because electrons are going to do whatever's easier. So After 18 total electrons in an atom, there is an overlap of energy levels. And so after you fill 3p, the next electron that's going to enter will enter into the 4s orbital instead of finishing up that third energy level by putting it in 3d. The reason for this is because of that off-ball principle. Electrons are lazy, and because it's easier to put an electron in 4s, that's what it's going to do. So here I have kind of our energy levels and increasing energy, and you can kind of see our little pattern that we had going on. 1s, then 2s, then 2p, then 3s, then 3p. And instead of an electron finishing up the third energy level before it puts electrons in the fourth, it goes ahead and puts a couple of electrons in the fourth energy level. Why? Because it's easier. And takes less energy. So it's going to put a couple of electrons in the fourth energy level. Then it finishes filling up the third energy level. But the weirdness doesn't end there. Then it'll put some more electrons in the fourth energy level. And then it will put some in the fifth energy level. Why? Because it's easier. Then it'll put some more in the fourth energy level. Then it'll put some more electrons in the fifth energy level. Put some electrons in the sixth energy level before electrons start finishing to fill up that fourth energy level. And again, it's because of the energy required to put those electrons in there. And electrons are going to take the easy way. So in order to write our electron configuration, we need a way where we can write these in order in which they are filled. And so what we're going to use is the periodic table. There's another video on that to show you how we use the periodic table to write our electron configuration.